And if the particle is standing, well, the particle is not standing still because all particles are in constant motion, random motion there. Okay. If it's in motion, it will stay in motion until there's an outside force to change that situation there. So that's an action equals to the reaction there. So that's the Newton's law there. So classical physics of Newton's law still governs the behavior of the gas particles under this assumption. And again, the distance between the molecules on average is much larger than the molecule itself. So that's something that mainly tells you when you have a container of gases there, the distance between the particles are much larger than the size of the molecule there. And also, the gas molecules are constantly moving in random directions there. They're not just moving towards one direction, they're always moving to all directions there. So you can imagine when you have billions of molecules compressed in a small container there, they're moving to all random directions there. They are colliding with one another. They're colliding to the wall of the container there. And when the collision happens there, there's a force exerted on each other as well as on the wall of the container there. And that is the source of what we call pressure. When they move, when they collide with the wall of the container, it actually generates a pressure. And we'll talk about the pressure a little bit later. So we also assume that since the particles are far apart from one another, now we know anything that makes up, any matter that we study is made up of atoms. Atoms are made up of positively charged particles, protons and electrons, and neutrons. Neutrons have no charge. So there will be charged particles within, well, smaller subatomic particles within the molecules of gases there. And then in theory, if they're close enough, the charged particles, they will attract and they will repel with one another, depending on the charges they bear. However, since the assumption that we made here, the distance between the particles are much larger than the size of the particle itself, we assume there's no attractive repulsive forces between the particles. Now that assumption is valid under, again, normal condition, high temperature, low pressure. However, if you compress everything into a very small container there, then they're so close to one another, you have to take that attractive repulsive forces into consideration. And that topic is in the last learning objective of this particular chapter there. We will look into the extreme conditions where you have very high temperature or very low temperature, very high pressure. How does that affect the behavior of the gas there? But for now, under normal condition, that is relatively high temperature, 25 degrees Celsius, and relatively low pressure, and anywhere between 1 to 3 atm. That's the pressure there. And then these assumptions would be valid for all gases there. And a gas that follows these assumptions is what we call an ideal gas. Now, anything ideal does not exist. So there's no such thing as an ideal gas. However, when we come up with these assumptions there, and using these assumptions to deal with real gases under normal conditions, the gas law that we develop under these assumptions is going to be valid under normal conditions. Okay, so that's something that we want to put ahead before we start dealing with the gas behaviors there. So our the 6 learning objectives in this chapter. The first one, we're going to look into how do we, when we study the behavior of gas, what do we need to know? Well, what is the barometer? How do we measure pressure? Okay, barometer measures the pressure there. And what is pressure? Where does it come from? What's the reason for pressure? What is what we call the standard temperature and the standard pressure? So this is something that we want to describe before we get into the gas laws there. The first learning objective, we will look at some of the things that we need to use to describe the behavior of gas there. Okay, now gas is there, and to describe a gas quantitatively, we have to have 4 physical factors. Okay, and those physical quantities, namely, are the temperature. When you change the temperature, the behavior of the gas will be different, and the pressure, okay, and the volume, and then lastly, the quantity of the gas. Now, the quantity of gas, or quantity of chemical, is measured in moles. So, pressure, temperature, volume, and the amount of gas in moles. These 4 quantities must be identified if we want to describe the behavior quantitatively describe the behavior of a particular gas. We have to know how much we have, how many moles of the gas we have. We need to know what is the temperature under which the gas is being studied, how much volume do they occupy, and also what is the pressure there. You can change any of those three quantities, the first three quantities there. When you change any of the three quantities there, when you change one, you will affect the other two. The number of moles will not change, okay? But the pressure and volume and temperature are dependent on one another. So that's what we're trying to get to. Now, when you measure temperature, and this is something that you're quite familiar, well, some of the scales that you're quite familiar with, it depends on depending on where you grew up here. Fahrenheit, that's a temperature, this temperature scale that we use in this country every time when we talk about the air temperature outside. We use Fahrenheit. And Celsius, that's another one. Okay. And then when you study gas behaviors, this is the scale that we need to use. We use the Kelvin scale or the absolute scale. Okay. The Kelvin scale, 0 degrees Celsius or 32 degrees Fahrenheit, is 273.15 Kelvin. So that's the freezing point of water, and then the boiling point of water, 373.15 Kelvin. Happens to be 100 degrees Celsius, 212 degrees Fahrenheit. Okay. Now, when you introduce, when we talk about the temperature scale, when we deal with the gas laws there, you need to keep in mind, every time the temperature is involved in a calculation, temperature has to be in Kelvin scale. We may give you the temperature in Celsius, and we may give you the temperature in Fahrenheit. And matter of fact, in chapter 2, I think in your textbook there, when we're talking about the dimensional analysis there, and in your textbook, there's an equation there. How do you calculate Fahrenheit, convert Fahrenheit into Celsius, and then from Celsius to Kelvin? That's something that we want to look at in this particular chapter. We will be focusing on the conversion between these two scales. Most likely, in this text, in this particular course there, we will not give you temperatures in Fahrenheit, ask you to do the conversion. Although Fahrenheit minus 32 times 5 divided by 9, that's the equation you use to convert the Fahrenheit to Celsius. And once you convert the Fahrenheit to Celsius, Celsius to Kelvin, the relationship is simple. Okay. Kelvin, temperature in Kelvin scale equals to the temperature in Celsius plus 273.15. Okay. So that's the number that you need to remember, and we will give you this information when you take exams there. But it's always there's always a benefit there. If you know this equation, if you know this relationship already, you don't have to look it up. And looking it up will take time. So that's something that you may want to memorize. The relationship between Kelvin scale and the Celsius scale, Celsius temperature plus 273.15 will give you Kelvin. So every time when you see a temperature in the question related to gas laws and the gas behaviors there, you need to remember temperature has to be converted into Kelvin. You add 273.15 to Celsius. Okay, so again, we cannot overemphasize this, because most of the time when you make mistakes in calculations, dealing with gas law problems there, you forgot to convert. Whenever temperature is involved, and if you make a mistake there, most likely it's because you forgot to convert it into Kelvin. So that's something that you always need to remember. Okay. The second quantity, pressure. Where does the pressure come from? Well, in physics, we know the pressure is a factor of force over area.